So welcome again, and we're going to have two more talks. And it's really nice. Professor Martin Jagi just entered the room over there. So he's also like another organizer of this meeting and a person who also sponsored some of our meetings and apéros at the beginning. So before we get some fundings from UnivGe, and this is the right slide this time with UnivGe and EPFL and Professor Martin as our sponsors. We also planning to change logo, thanks to Martin, for something more modern, and you're gonna to find it on our videos, which gonna to be released next week. So right now, we're gonna to have our fifth speaker today, David Droz, and he's just recent master student from EPFL, and he was specializing in cosmology and gamma ray or gamma ray emissions detection, and it's a really interesting topic as you need a very special detectors. You can ask him for more how it is done to detect. It's not like a normal light. And now he is doing his PhD in University of Geneva, where he is working still on cosmic ray physics and the dark matter physics particle experiment, and abbreviation is DAMPE. And they are basically responsible for providing us a beautiful picture for our poster. And David will explain much more about what it is. And by the way, it's a person who is also trying to be involved in online courses, because as I know, he did the translation from astrophysics course on MOOC at EPFL and provide English subtitles. And he did like 3 or 6 months internship in Lastro? 3 months. 3 months in Lastro, which is a part of EPFL working exclusively on astronomy and under Professor Kleb, yes?
It was Professor Melon.
I'm sorry. Welcome to David, and please enjoy his presentation.
Okay, hello everyone. Thanks, Pavel, for the introduction. This talk will be some application of machine learning techniques to fundamental physics, and more specifically to particle physics and cosmology. So I will first need to do some physics introduction. I know this is mostly a machine learning talk, so I will try to keep it brief yet interesting enough. But I know there are some dark matter specialists in the audience, so they will feel right at home, I think. I will present the DAMPE experiment, which is the toy we're playing with to hunt for dark matter. And I will present what we can do with machine learning, the performances we get, and the challenges we face when trying to apply it to our very particular data. So first, I think I need to say what are cosmic rays. So cosmic rays are some kind of space radioactivity. They were discovered by this gentleman, Victor Hess. We noticed that there is more radioactivity at high altitude when flying with a balloon than when on the ground. Cosmic rays are high energy particles that come from outside of the solar system. They are made of protons, atomic nuclei such as helium, carbon, and so on, as well as some other like electrons, photons, and so on. The sources are typically supernova remnants, supermassive black holes, and all that kind of very interesting stuff that you find in the universe. They reach extremely high energies, which make the Large Hadron Collider at CERN look like a toy, basically. I cannot talk about space without showing some pretty pictures. So on top are artist impressions, on bottom are real images taken by telescopes, space telescopes actually. On the left are pulsars. So pulsars are some remnants of a star that went supernova, that exploded, and they leave some very small object, extremely dense, with a very intense magnetic field that we suspect can accelerate particles to the energies we observe. Here are active galactic nuclei, quasars, which are basically a supermassive black hole with matter falling onto it. So as matter falls on the black hole, it gets super dense, it gets super hot, and it gets so shiny that the galactic nucleus outshines a full galaxy and even outshines several other galaxies that you can barely see in this picture. Then there is the dark matter problem. Dark matter is hypothetic matter that should form 80% of the mass content of the universe. We only observe it indirectly through its gravitational interaction. For example, on this plot to the top, we notice that galaxies rotate much faster than what we expect them to do, and this hints towards missing mass. There are a lot of indirect evidences for dark matter, which would take me hours to list. But anyway, the point is that we have some unknown matter that we suspect is made of elementary subatomic particles that we're trying to hunt for them. We expect to detect them through either one of these three different methods, which I list here only for the sake of completeness. The main method we're interested in this talk is indirect detection. So the idea is that when you have two dark matter particles that collide somewhere in space, they could produce regular matter, which we could detect from the Earth orbit. For example, they could produce electrons, an electron-positron pair. And if we had some detector in space that would detect an excess in electrons, then this would be a strong hint toward dark matter. And to do that, we have a very nice toy. This is the Dark Matter Particle Explorer. It's a spacecraft of the Chinese Academy of Science and the result of an international collaboration between China, Italy, and Switzerland under the leadership of the Purple Mountain Observatory in Nanjing, China. It was launched in 2015 by a Long March rocket. I posted here the link to the launch video, which is always pretty to see. The main objectives are the study of cosmic rays, some high-energy gamma-ray astronomy, and the holy grail of this experiment would be the detection of dark matter particle. DAMPE is a system of 4 detectors. So I think I need first to tell how a particle detector works. The idea is that when a charged particle flies through material, it can ionize the material due to its electric field. This ionization will free electric charge in between the atoms. And this electric charge can be read by some electronics. So then we can map an event, a single particle, to a digital signal. For example, here I show if you have several layers of materials and you detect interaction points one after the other, you can trace back where a particle came from and how it decayed through the detector. This shape basically is called a shower because, well, you see, if there were more interactions, it will keep growing new branches, and this could look like a shower. The main detector is this calorimeter. The calorimeter is a very dense detector with the goal of having a single particle deposit all its energy inside it. So we want the full interaction to happen in a single detector, so we can trace back how the interaction looks like, and we can identify the particle. This detector is made of 14 layers with alternating orientation. So when we have a particle interaction inside it, we can get some kind of three-dimensional picture out of the interaction. To detect dark matter, we are interested in electrons. because we have many models that predict that dark matter particles should produce electrons. So on the left here is how an electron forms a shower. You have an electron that could interact with some atom here. This really is two particles, and they themselves interact later down, releasing a ton of particles, an exponentially growing number of particles. And this looks like these strange figures. Electrons have a very narrow and short shower, while this is in comparison with protons that have a much bigger shower. We want to identify electrons. So this is a binary classification task with the background being protons, and it's severely imbalanced as there are 100 times more protons than electrons. This is how the events look like in our detectors. So here the particle comes from the bottom and moves straight up. We have an XZ view, YZ view, so these two are the same event. And you can see, maybe not that much, that the electrons stop pretty early in the detector while protons fly all the way through. So this is how we make the difference. However, you can see that, well, without a trained eye, this is impossible to see which one is which class. And in fact, even for the trained eye, here I know there are electrons and protons because those are simulated events. I specifically asked the computer to produce me an electron and a proton. Otherwise, I would only be able to tell the probability that this is either particle, and I wouldn't be able to tell for sure what it is. This is in contradiction with many machine learning applications where we expect the human experts to have a near perfect classification accuracy. Here we don't. So how do we make, in classical methods without machine learning first, the separation between the two classes? We build some variable, which we call zeta, which combines the width and the spread of a particle shower. Hold on. Retrospect notification.
Sorry.
Yeah. So this variable basically describes the shape of the interaction and allows, wrong key, to split the phase space of our events into two classes, which you see here. And you see that zeta forms a sharp peak at very low values. Those are electrons. And protons go to very high values in a much broader way. This allows us to make the difference between the two classes. And using this method, we were able to publish a first electron flux. This was published in Nature a few months ago. And the main result is basically the observation of this, of what we call a break. So our data points are in red, and you see that in the middle area it's basically flat, and then it drops suddenly. This is what we call a break. It was the first direct detection of this break. But there's still some work that needs to be done. You see that at very high energies, the uncertainties get much bigger. It's basically bigger error bars here. And, well, there are two causes for that. The first cause is the lack of events, since this is only 1.5 years of data, and high background contamination. If we want to improve that, we need a better way of classifying events. And I suppose you all see where I'm coming at. Let's see what we can do with machine learning. So some preliminary studies were made before publishing the previous result with principal component analysis and decision trees. And it was found that they didn't provide a significant improvement over the zeta variable. But lately, the trend is not really that. It's mostly neural networks. So maybe we can do something with neural networks. We have two potential approaches. We could, for example, take an event in our detector and build it as an image. That way, we would have a pattern recognition problem, and we would use the convolutional neural networks that were presented earlier. Or we could go to a simpler approach and build an event represented through, let's say, 50 high-level variables and feed them into a single-dimensional vector to feed-forward neural network, which is really simplest neural network you can think of. So here I'm taking the second approach. If I have time at the end, I will talk a few words about convolutional neural networks, but what I will present here is this approach. Step 0 of applying machine learning is identifying the data we're working on. Arguably, this is an even more important step than building the model or training it. In particle physics, we typically have 3 data sets. They all originate from the same laws of physics, but then they split with several differences. First, we build with our current knowledge of physics, we build computer-simulated data. This is typically the training and testing set of our machine learning algorithm. Then we have some laboratory experiments where we have only a model of our detector, and we get some calibration data, which we can use for testing and evaluating the method. And finally, once everything is ready, we launch the satellite, and we have the real data, which we call flight data, and this is the application. Once the satellite is launched, of course, there is no coming back. So what we really want is to study the application data using the simulated data, which might exhibit some differences. Of course, an advantage we have with this simulated data is that we can always produce more of it by simply having some CPUs running for a few hours. So to select the data, I extract 47 variables out of the calorimeter I showed you earlier. I normalize them to the 0-1 range. This is typical for neural networks, as they need a standardized input. And I have a one-dimensional array of 47 variables for each event. We train and optimize on the simulated data, and then we test and evaluate how it works on the calibration and flight data. Some numbers, some details of the neural network architecture. This is an extremely simple neural network, probably the simplest out of what everyone here is working on. It's only 4 layers, starting with 200 neurons going down, 20% dropout, trained on 1.2 million observations over 100 epochs. The software I use is Keras 2 with Ciano as a backend, and I'm using hardware provided by the University of Geneva. With the NVIDIA Pascal P100, I have some half an hour training time. And once all this training is done, what we want to see are the performances that we have. So on the left, we have the classical ROC curve, which shows that the neural network significantly outperforms zeta. Zeta, again, is our classical method to make the difference between electrons and protons. On the right plot is the same information, displayed only differently, where we show, well, this is a log scale. We show that at 95% true positive rate, we get 10 times lower false positive rate. So this is a really significant improvement, which basically shows that zeta is now obsolete in comparison to the neural networks. So well, now that we have that, we want to apply it. So we know that the neural network outperforms zeta. We have a ROC curve that gives me true positive rate, false positive rate. I should have everything I need, right? However, again, the training data is different than the application data. So the metrics I get out of my ROC curve are likely different on real data. So this could introduce a certain uncertainty that with the level of accuracy we're working on, we cannot afford. So what we want to do is evaluate the true and false positives from the real data, which is unlabeled. Here's a short example of mismatch between simulations and calibration data. Those are extreme examples. Most of the time, the match is much better. However, you see that while the general idea is conserved, there are still some differences in the distribution, which means that it could throw off the accuracy of the neural network. So how do we try to evaluate the performances on real data? The neural network produces an output between 0 and 1, which is the probability of it being an electron. So what I do here is I simply make an histogram of the values, and we recognize immediately a peak at 0 and another peak at 1. So those are my background, those are my signal. And from the look at it, I should be able to extrapolate. Right. I simply take the curve and I prolongate it, and then I have an estimation of my amount of background in the signal region. So I should be able to estimate my false positive rate out of this extrapolation. But if I compare that with the simulated data, we see that this extrapolation is a bit naive. You see here that there is a peak of background in the signal region. So it's not monotonous. I cannot directly extrapolate because there is a plateau and then an increase. This peak should appear somewhere here, but I do not know the magnitude of that peak because, again, simulation and application are different. So I cannot make this extrapolation. By the way, this peak is a feature which I tried with several different machine learning techniques, even with decision trees or linear discriminant analysis, and this peak always appears. This is a feature of our data that some background events really look like signal events. So where does that peak come from? It actually comes from the output layer of the neural network. So as a reminder, the last neuron of a neural network applies the sigmoid function to its input. The sigmoid will crunch the output to the 0-1 range. So we can represent a signal as a probability. However, we have limited floating point accuracy. The sigmoid of 40 is equals to exactly 1.0 using 64 bytes float. But then this means that the sigmoid of 200, of 300, of 1000 give the same value. So we're losing information here because different inputs lead to the same output. We could try to remove the sigmoid and see what happens. If we do it, we have a significantly different shape. We see a peak of background at -10, -20, and a peak of signal in the positive numbers. And here, what's really interesting is that the extrapolation I showed earlier can actually be performed. As you see, here the behavior is monotonous. So the extrapolation is straightforward. This is fly data. And you see, by the way, that the shapes do not exactly match. However, I still have my two-peak structure, and I can make the extrapolation to estimate the number of true positive, false positive, true negative, and so on. What's even more interesting is that here, suppose I take all the events that are above 40. Here, I have a pure signal sample. I do not have any false positive if I select a slice here. While in the previous case, I could never select a pure sample of either signal or background. So here I gain in usability. But of course, I removed an activation function. You expect some degradation of performances. Actually not. The row curves overlap. And well, here is a very zoomed in. If you keep zooming in, you will still see an overlap. They have the same area under curve. And again, better usability since I can select slices of my data. Of course, now it's harder to map that into a probability because I don't have a number in the 0-1 range. So next step from that is we could try to further improve the matching between training and application, which was the original problem. Here I list some ideas, which would be typically controlling the amount of information that I feed into my neural network, moving to convolutional neural networks, which might be less sensitive to high-level variables that we build, using generative methods with variational autoencoders. This could typically shift the distribution of true variables into the distribution of simulated variables and should, in theory, improve the matching. Or maybe nothing at all. Maybe it's not even needed. This is still a work in progress. Keep tuned on that. Then there is another issue which I go over very quickly. Basically, the number one rule of software development is make sure that whatever you do, your colleagues can use it. And in particle physics, it's very difficult because particle physics use C++ and the root framework, which is a very specific framework using some hybrid C++ style. And our experiments use very outdated C++. While I, on the other hand, was using latest version of Python, latest version of Keras. And so if I produce some results with Python, I have to make them available to my colleagues. There are some alternatives for high energy physics here that I list. And this constraint leads to this weird flowchart where I basically have to convert from the input C++ styles to Python readable format, do all the machine learning, and then convert back. There is this PyRoot library that works for high energy physics, but it's a very time-consuming step. So while this serves only as a reminder that whenever you start working on a project, make sure that your colleagues will be able to use whatever you produce. These are my conclusions on this talk. As I think we all expected, neural networks significantly outperform our classical analysis. There are some issues with the application, but we can always find some workaround those issues. Workaround that I hope you found interesting and maybe that you can apply on your own research. So this is all from my side. Thank you for your attention.
So please ask questions because we momentarily lost the microphone.
So yeah, I have a question. You say you have basically three main data sets, right?
Yes.
Simulation, laboratory, and real stuff. So from what I understand, right, there's no way you can label that you're human the real data, and it's impossible, right? But what about the second one, the laboratory data set? Is it something that you know what it is? Is it labeled?
Yes. So because this the second one happens at CERN facilities where we have a particle accelerator.
You send a particle.
Exactly.
What particle is
Exactly. We can always choose what kind of particle we accelerate and we send to our model. However, it's very limited because time in those CERN facilities is very expensive. So we have low data, and it's at a very specific energy. We don't cover all the energies and all the features that we expect in orbit.
So what is a bit fascinating here is that at the end of the day, you don't really know if your model is good or not. Because, I mean, how can you prove that the real data you're right?
Right, well, we can always see, where's my spectrum? In the very final result, if I get a spectrum that matches with other experiments, then this is a strong signal that I have something good, right?
Using that approach you published in that paper because you see this break or something like that?
Yes,
okay.
Yes. Well, here you see the matching, but then we will have to produce a new flux using neural networks, and then if we get something matching, we immediately see that we have that the model is good.
Yeah, okay. Thank you.
So, unfortunately, we are a little bit over time, so I would encourage you to ask questions on upper, and we're going to start with the next presentation.